So here's problem 2 of the vector homework, and you can see that it asks you to find a number of quantities. So we're just going to start with the first one and basically crank through these things. The first quantity they ask you to find is the resultant vector of a move 5 feet to the right and 17 feet up. And just a little bit about coordinate system. You probably remember this from high school mathematics, but if you've forgotten, we'll just review it here. There's the Cartesian plane named after Descartes, and on the Cartesian plane, the axis, there's this vertical axis, we call this the y-axis, and there's a horizontal axis we call the x-axis, and where the two of them intersect we call that the origin, and the origin has the coordinates 0, 0, right? So 0x and 0y. Moving right along the x-axis is considered a positive move. Moving left along the x-axis is considered a negative move. Moving up on the y-axis is considered a positive move. Moving down on the y-axis is considered a negative move. Why do they have those conventions? I don't know. That's just what Descartes decided on, was that was how we were going to label our frame of reference. The other thing that's important for this problem is to understand angles. So by default, we consider straight east or straight right 0 degrees, which is a little bit different than if you think about like compass directions. And angles in the Cartesian plane proceed counterclockwise from that 0 degree mark, so that the y-axis is at 90 degrees. Then if we came another 90, the negative x-axis is at 180 degrees, and the negative direction on the y-axis is at 270. And then, of course, if you came all the way around, you'd be back at 360 degrees, would be a full circle. So let's think about this first problem. What does it say? It says, well, first you walk to the right 5 feet, right? You make an x move, positive 5 feet. And then you walk upward, or northward, a distance of 17 feet. And really what it's asking is that if someone wanted to start where you started and finish where you finished, but instead of taking this rectilinear path, or this basically two-component 90-degree path, they just wanted to cut diagonally, what would be the length of that path and what would be the angle relative to this 0 degrees in the Cartesian plane? Well, you don't need trigonometry to figure out the length, because by definition the y-axis is perpendicular to the x-axis, so this is a right triangle, and then we can just consider these sides A and B and this hypotenuse C, and you can go back to middle school and you can use Pythagorean theorem, right? So let's calculate the length of this. Well, 5 squared plus 17 squared equals c squared. Now, how do you untie the knot? Well, we're trying not to get c squared, we're trying to get c, so we just simply square root both sides. And I know what you're thinking. It'd be tempting to say, oh, square root of 5 squared. Well, that's just 5. Let's just cancel the exponents. But you can't take the root of parts of sums. In other words, you have to turn the crank on this and actually get the sum to take the square root. So let's do that. It's going to be the square root of, and then let's use the calculator to figure out the number. So 5 squared, that's 25. 17 squared is going to be just short of 300. That's 289. If we add the two of them together, we get 314. So the square root of 314 equals c. Now, 314 is not an easy number to take the square root of, so we'll use the calculator. And again, on this calculator, the easiest way to do that is to raise it to the 1/2 power. And we find that the length c is about 17 3/4 feet. So about 17.72 feet. Now, you know, you can ask yourself, is this reasonable? Well, certainly it is not going to be as long as the path where you took the square corner, right? So if you think about 17 plus 5, that would give you 22. C has to be less than 22. On the other hand, because C is a hypotenuse, and by fundamental geometric properties, the hypotenuse is always the longest side, it has to be greater than 17. So it has to be larger than 17, it has to be less than 22, and this answer satisfies that. So it tells you that it's probably reasonable. Now, perhaps a little bit more challenging question is, okay, what's this angle? Well, let's give that angle a name. Let's call that angle theta. Well, what do we know about this triangle? We actually at this point know all three sides, but remember that two of them were given, two of them were measurements, and one was a calculated value. And we'd always prefer to work off of what we'd call an empirical value, a measured value. So we want to relate this 5-foot side with this 17-foot side. So we think about, here's the angle, we have an adjacent side and an opposite side that we want to relate. And the question is, how do those relate? Well, think back to just basic trigonometry. So, ka, toa. Well, the only one of these functions that relates opposite and adjacent is the tangent function. So, what we know is the tangent of angle theta equals, let's see, opposite over adjacent, 17 over 5. Now, tangent tables are not given in fractions, they're given in decimals, so let's convert that to a decimal just by simply using the calculator to do the division problem. So we're going to clear this out. 17 divided by 5 is 3.4. So the tangent, 3.4. The tangent of angle theta here is 3.4. Now, the problem is, if you think about the key you've used on your calculator, that was a key where you put an angle in and it gave you a ratio of the opposite to the adjacent when you use the tangent key. But here you have the ratio of the opposite to the adjacent, and you're trying to find the angle that produces that tangent. So you have a couple of options. One option is you could go to the trig table and you could look for that ratio. And so if you notice, we'll start at the top of the trig table here in the tangent column, and we'll come all the way to the bottom, and you notice that the highest tangent number we get is 1 at 45 degrees. But remember that this table can be read in two directions. So if we come over here, if we start on the bottom of the table, you see the tangent column marked again, which starts at 1 and proceeds to much larger numbers. In fact, actually eventually proceeds to infinity. So we're looking for 3.4, if I recall correctly. Yes, so let's see what 3.4 in the tangent column corresponds to. Well, the closest angle that we're going to find in the tangent table here, because we're starting on the bottom, we actually have to read this right side column, so we come from 3.4 over to about 74 degrees. And that's reasonable, and I want to talk about for a moment why that theta should be approximately equal to 74 degrees. Well, the reason that it should be, that 74 is reasonable is that think about if theta was 45 degrees. What would be true about the lengths of these two sides? Well, a triangle with a 45 degree angle, a right triangle with a 45 degree angle between the hypotenuse and one of the legs is an isosceles triangle, which means that the two legs are equal length. Because the leg opposite this angle is substantially larger, we would expect an angle that's a good bit larger than 45 degrees. So this is a reasonable number. Now, there's an alternative approach at arriving at that number, and it involves using inverse functions on the calculator. So I want to talk for just a minute about functions. So, you know, a function, you can think of a function as a machine that you drop stuff in one end and you get something else out the other. So let's say that this is the times 2 function machine, right? So you drop a 3 in this end. What comes out the bottom end? Well, 6 comes out, right? You drop a guy in this end. Little guy jumps in this end of the machine. What comes out the bottom? 2 little guys. You get the idea. An inverse function is a function that undoes that. So if I had an inverse function machine after this, okay, so I'm just going to put times 2, and then I'm going to note raised to the -1 just to indicate that it's inverse. So if I drop this 6 in the inverse machine, what does it do? Well, it undoes the original process, and it gets me back to 3. If I guess we'd have 2 little guys that came out of the bottom of this times 2 machine. If those 2 little guys jump in the inverse function machine, what do you get? You get 1 little guy. So the story is, you've already been using functions. You've been using the tangent function machine, right? So what do you put into the tangent function machine? You put an angle in. You put theta in this end, and out this end you get this ratio of opposite over adjacent. The inverse function, you're going to put the ratio of opposite over adjacent in, and what are you going to get out? You're going to get theta out, right? Theta is going to be your output. You're going to get an angle out. So to use an inverse function in the calculator that's on these computers, what you would do is you'd hit the INV key for inverse. Now some calculators will actually have a key for the inverse tangent, and it's called the arctangent key. And what the key will look like is this right here. It'll be tan to the -1 to indicate that it is inverse. So how do you use this? Well, you take the ratio of the opposite side to the adjacent side, which we already figured out was 3.4, and we hit arctangent, and that's going to give us an angle in degrees. So you'll notice that by looking in our trig table, we had predicted about 74 degrees, and you can see that the calculator agrees with this. If we did a precise calculation, theta is equal to 73 point, we'll round at 2 decimal points here, 73 and change degrees. My calculator doesn't want to load. So the answer to the first question here is that for A, the vector has a length of 17.72 feet, and it's at the angle relative to 0 in the Cartesian plane, 73 and change degrees. 73.61 degrees. And that would be the solution to problem 1. Now let's look at problem 2. Problem 2 represents a series of forces, and the first force is -8 pounds, which means an 8-pound pull to the left in the x direction, and a 3-pound pull vertically in the y direction. And again, it's an upward pull because 3 is a positive number. 3 pounds. So as I've drawn this free body diagram, you can see that the vectors are tail to tail, and the first step to sorting this out is to getting them head to tail. So I'm going to slide that vertical vector over so that these are now head to tail. So that's 3 and that's 8. The resultant of these two vectors is going to be a vector that projects upward and to the left. And if you think about it, that makes sense. If you're pulling up with one rope and you're pulling to the left with another, that's equivalent to an individual rope pulling up and left with some magnitude of force at some angle. So again, how do we calculate the magnitude? We just can simply use Pythagorean theorem. So 3 squared plus 8 squared, and then we'll take the square root of that. So 3 squared is 9 plus 8 squared. 8 squared is 64. Take the sum and take the square root. And we find that the equivalent force is about 8.5 pounds. We'll say 8.54 pounds.